So recall with our discussion of gases, gases are composed of particles that are moving really fast in random directions, and the particles are spread apart from each other as possible. And gases have four basic properties. First property is pressure. And pressure, remember, is a measure of collisions between the particles and the walls of the container. The more collisions and the more forceful those collisions, the higher the pressure of the gas. We can also say that a gas occupies a certain volume because gases are going to occupy the space of the entire container that you put them in. So the volume of a gas is dependent upon the size of the container that contains that gas. Another property of a sample of gas is the actual number of particles that you put into the container. So the actual amount or moles of gas particles in the sample. And then finally, the fourth property has to do with how fast those particles are moving, or what we refer to as average kinetic energy. This is a measurement of temperature. The faster the particles, the higher the temperature. Or if you lower the temperature, the slower the particles are going to move and the less kinetic energy that they have. So now take a moment to copy down this chart summarizing those four variables of a gas sample. You have pressure, volume, the amount, and temperature. One thing I do want to point out to you are the units that we use to measure each one of these variables. Pressure, we're going to measure in atmospheres, abbreviated ATM. Volume is going to be measured in liters. The amount, or how much gas you're putting into the container, we're going to be measuring that in moles. And then finally, temperature is going to be measured in Kelvin. So every sample of a gas has all four of these properties. And there's a certain relationship between these four properties, and we call this the ideal gas law. This law, or commonly referred to as PIV-NERT, allows us to predict the pressure of a certain gas sample if we know the volume of the container, if we know how many moles of gas are in the container, and if we know the temperature. Okay, so please record this ideal gas law equation into your notes. This is going to be our main equation that we use to do some gas law calculations. Now, we have P, we know what V is, we know what N is, and we know what T is. So you might be asking yourself, what is this R in this ideal gas law equation? So R is referred to as the gas constant. This gas constant is a constant, meaning it doesn't change. So R is always going to have a value of 0.0821, and the units of liters times atmospheres divided by moles times Kelvin. And don't let those units scare you. It's just very important that we do know the units of this R constant so that we use the correct units of pressure and volume and the amount and temperature. So because our ideal gas constant R has these units, that's why we have to use these units for our pressure, our volume, and our amount and temperature. So let's go ahead and take a look at some example problems. Please record the question into your journal. Hit pause if you need to. Okay, the first thing that I like to do when I'm solving ideal gas law problems is I like to list all those variables off to the side in the order that they appear in the ideal gas equation. So it's P, V, N, R, T. or PivNert, as we commonly say. Now I'm going to go ahead and plug in the numbers that I know. And the first one that I'm always going to plug in is R. Because R is that constant, I will always know the value of R. It's 0.0821 liters times atmospheres all over moles times Kelvin. And then I'm just going to go through the rest of the problem and start recording my information and labeling. So we have 0.453 moles of a gas. That is N. So N equals 0.453 moles. This gas is confined to a 12.5 liter container. That's going to be our volume. And it exerts a pressure of 1.24 atm. So that is pressure P. What is the temperature of the gas? So they want me to solve for temperature. That's the unknown. Okay. So I have all my variables listed here off to the side. Before I do any math and work with the ideal gas equation, you always want to check your units. Please make sure the units are consistent with the units found in R. So for example, pressure. Pressure in R is in atm. So that means the pressure that I use in this ideal gas law has to be atm, which it is here. So we're good with our pressure units. Now moving on to volume. The volume unit inside the R is liters. Our volume is in liters. That's perfect. Our amount has to be in moles, which it is. So we're good. And then finally, temperature. I don't have any unit of temperature in the question, but if I look at my R value, I know that temperature has to be in Kelvin. So this is really going to help me out when I get to my final answer. I don't really have to think about units anymore. I look back over here at my list. I know I need to make temperature in Kelvin. Okay, so the next step is I would like to write down the ideal gas equation. And I am solving for T, temperature. So we're first going to rearrange this equation and solve for T. So I'm going to divide both sides by NR. So NR cancels. So T is equal to PV divided by NR. Now it's a plug and chug. I plug in my numbers into this equation and I solve for temperature. So we plug in our variables, and I am putting the units here just so you guys can see that they're going to cancel out. I got atm here on the top, cancels out with those atms on the bottom. Same thing for the liters and same thing for the moles. So this also is another way that you can figure out the unit that should be on your final answer. In this case, it's going to be Kelvin for temperature. So I finish up the math here. So I've multiplied the top, I've multiplied the bottom, and now we're going to divide. Get an answer of 416.76. And I look back and see what my unit should be. Should be a capital K for Kelvin. One final thing, we're going to round for our sig figs. I go back and look at all my given numbers in the question. The fewest number of significant figures was 3, so we'll round this to 3 sig figs. So that means our final answer is 417 Kelvin. All right, let's try a second example. Go and hit pause, give yourself some time to record the question into your journal. I'm going to start this problem in the same manner. I'm going to list my variables off to the side. The one variable I know automatically is R. It is always 0.0821. The problem states a gas exerts a pressure of 1.5 atm in a 5.0 liter container at a temperature of 25 degrees Celsius. How many moles of gas are in the container? So they would like for me to solve for moles of gas. So that's going to be our N. Now, before I set up my equation, please check your units. Make sure your units are correct. Based upon your R, pressure needs to be in atm, which it is. Volume needs to be in liters, check. N needs to be in moles, yes. And then temperature needs to be in Kelvin. There's a problem here. Our temperature is in degrees Celsius. So we first have to convert our 25 degrees Celsius into Kelvin before we move forward. Remember that we're going to add 273 to our degrees Celsius to convert into Kelvin. So this gas has a temperature of 298 Kelvin. Now we are good for our unit. And we're just going to box what we're solving for. Our final answer should be in moles or the variable N. Okay, write out your ideal gas equation, PIV-NERT. And we're going to rearrange this so that we solve for N, divide both sides by RT. So N is equal to PV over RT. And now we're going to plug in our numbers into this equation. We have our values substituted in. Now we're just going to simplify a bit. Now we're going to divide, and N equals 0.30655. And looking back at my list, I should see that N needs to be in moles, or you can look at your substitution of your values into the equation. You'll see that atmospheres cancel, liters cancel, Kelvin cancel, and then the only unit that you're left with is mole, so your answer has to be in moles here. Finally, rounding for sig figs. Again, go back and look at all the given numbers in the question itself. The fewest number of sig figs in this question is 2 sig figs. So we're going to round our answer here to 2 sig figs. Keep the 3, keep that 0, but there's a 6 behind it. So we're going to round up. 0.31 moles is our final answer.